Next, let's do example 8. But before that, let's look at some formula that the book has listed. Okay. Now, for complex numbers, there is some rule that says that if you have two complex numbers, which is given by z1 is r1 cosine theta 1 plus I theta 1, and z2 is r2 of a similar thing, right? Then z1 times z2 as in multiplication will be equal to r1 times r2, and then cosine of theta 1 plus theta 2, and I plus I of sine theta 1 plus theta 2. Now the exact proof of this stuff is we're gonna skip that, because this part is not, we're not really focusing on complex numbers. We're just focusing on using trigonometric formulas to do stuff. Okay, and one of them is there's a part of complex numbers that use trigonometry, and that's what we're doing it right now. And as a result, we're not going to explain in detail what all this even means. I just want to show you that you can do this. And so that's our entire focus, is just follow the formula, well, a bit blindly, just so that we can get it to happen. Now the product is quite easy to do, in the sense that the rule is you multiply the r's together, okay, and then you add up the angle. So with that knowledge, then let's look at example 8. Example 8 says that z1 is 4, says 80, and then z2 is 2, says 145. So by the formula we just learned, then z1, z2, which is what we're trying to learn here, trying to figure out here, is equal to this times that, which is 8, and then CIS, the angles are added together according to the formula, so 80 plus 145, that would be 225 degrees. And that should be the answer, right? And so that is that. Well, the book goes a little bit farther and want to calculate what it is exactly. That is, what is cosine 225 and what is sine 225, which I suppose we could do that just for no reason. So that equals 8. If we write it out, then it becomes, the CIS becomes cosine of 225 degrees plus I times sine of 225 degrees, 225. Now to figure out exactly what that is, we can just use the calculator, or we can do this in our heads. Now the 225 is 180 plus 45 degrees. So the reference angle is 45 degrees. And 45 degrees has the 1 square root of 2 ratio. Okay? And so that will be equal to 8 times cosine 225 will be 1 over square root of 2. 1 over square root of 2. And not just that, this one is negative. So because it's on this side, okay, on the negative side of the x-axis. So the 1 is negative. So it would be negative plus plus the sine of 225 is this 1 over square root of 2, and this one is also negative because it's down here instead of up there. So the y value is also negative, so it's minus 1i, and divided by square root of 2, and that will be the answer. And we can also change this. 1 over square root of 2 is the same as square root of 2 over 2. Okay, that is the radical manipulation. Once you do that, you can also cancel out the 8, and so it becomes 4, and that is the final answer. I would think that leaving it like this should be equally valid. Okay, it's just 2, and this is the polar form, and the other one is rectangular form. In fact, it even says find the product. Yeah, it didn't really say that we have to turn it into rectangular form, but the book did it, so we'll do it as well, just for no reason. So that is example 8. Now next, let's look at example 9. The example 8, we did the multiplication of two complex numbers. So example 9, we're going to divide. And so flip over to the next page, and you notice the division, as you might imagine is just similar to multiplication, except that now instead of multiplying the two r's, now we divide, and then the angles, instead of adding, is being subtracted as shown in the book. So as you can see here, to divide the two complex numbers, like z1 divided by z2, then it equals r1 divided by r2, and then the angles are being subtracted. The first one subtracted by the second one, and that's about it. So knowing that, then let's look at example 9 on the next page. So I have written down example 9 right here on page 965. Z1 is 2 times CIS 213, and Z2 is 4 times CIS 33. And therefore, Z1 over Z2, following the formula, Z1 divided by Z2 is equal to the r's dividing by each other, 2 over 4, and then CIS, the angles subtracting each other. So angle will be 213 minus 33. Okay, I am following the formula that's right on top of this page that I showed you earlier. So let's focus. See, the formula says dividing the r's and then subtracting the angles, and then you got it made. So that's what we have here. Now so that equals to 1/2 times what is that thing? 213 minus 33 degrees. That's 180 degrees. Now 180 degrees is a bit special, okay? Because 180 degrees is equal to -1 for the cosine part. So that's just -1, and then plus I times sine of 180 degrees is 0. So it's times I equal. So the I part is 0, which means that the whole thing then equals to -1/2. See, that just because being that thing is 0, so we only got the -1/2 right, which is correct, okay, as the book says. So the next part, we're going to take the power of the complex number. A power just means the same as all other powers. That is, it multiplies itself so many times. Say if a z is, say, the power of 3, that means there's 3 of them multiplied together. Z times z times z, right? And then if it's 100 power, then you have the z times z times z times z, and do that 100 times, and that sort of thing. Anyways, there's the Moivre's theorem is says that to do a complex number raised to some power, what you have to do is you raise the r to the power n, and then you multiply the angle by n, and that's it. That is the formula. Okay, so keep that in mind for a bit, and then we will try to do that in the next example, example 10. Let me write it down. So I got example 10 right here on page 966, where we have 1 plus I to the power of 5, and we're supposed to come up with this thing with the Moivre's theorem. Now, however, that theorem is only if this thing is in polar coordinates, but this is in rectangular coordinates. So let's turn this thing into polar by drawing it out. Okay, where's 1 plus I? So here's 1, and this is I. So 1 plus I is right here, which means R equals to 1 plus 1, and the square root, r is square root of 2, and then theta is equal to pi over 4, right? That is, this is theta, and that is pi over 4. So that equals the same as r, which is square root of 2, and then CIS pi over 4. And that is the polar representation of 1 plus I. And this, of course, this whole thing had better be raised to the 5th power. And to do that, then we follow the formula that we just now looked at. Let's look at it again. Okay, it says that once something is in polar form, then the complex number, you raise r to the power n, and then CIS theta multiplied by the number n. So we'll do exactly that. So then this equals the square root of 2 will be raised to the power of 5, because 5 is what we're shooting for, and the CIS, and then 5 will be multiplied by the pi over 4 business. And this is the answer to whatever it is. What are we looking for? Oh yeah, the 5th power, and that should be the answer of it. Right, and so what does the book have? The book has, well, the book has the same stuff, but it also multiplies some of it out. So once we have the book got to this part, okay, and then it got into more details, as in what is cosine of 5 pi over 4. So please do this part yourself. What is cosine of 5 pi over 4 anyway? And then figure out what sine of 5 pi over 4 is, and that they're both negative because again they're in the third quadrant. That's why. But either way, okay, figure this out and then do the radical multiplication to come up with this answer yourself. Okay, and so that is that. And so the next part we're going to do is finding the roots after I clean off the board. Okay, so next let's consider taking the root of a complex number. Now as I have mentioned before, that this section is about using trigonometric functions in different circumstances. So what exactly that means to take the nth root of a complex number, we don't have to dwell in that right now. Okay, right now our goal is just to look at the formula and then apply it and use our trigonometric skills to follow the formula exactly and find the solution without really caring what it even means. So the nth, normally when you say the cubic root of say 27, you know it's 3 because 3 times 3 times 3 is 27, and 3 is the only answer. And there is no other answer, and that can multiply itself 3 times to become 27. However, in the complex number system, every number has as many roots as is power. That is the nth root will have n roots. Okay, like the cubic root will have 3 answers, and the square root will have 2, and the fourth root will have 4 answers, and so on. Why that is, you don't have to think about that or what that even means. That's not important to us right now. Right now, we're just going to try to follow this formula right here. That's in the book on page 966. Okay, and where example 11 is. And so to do the example 11, we need to follow this formula right here, which is slightly more complicated or tedious than what we have been doing. And what does this mean? This means that we have the nth root has n solutions, and the solutions are written like this. What that means is that it will start counting where k equal to 0, and then 1 and 2 all the way to n minus 1 in this location right here. So you have n solutions to write following this formula right here. So k will increase 1 at a time from 0 all the way up to n minus 1, and that's your n solutions. Now exactly what that means, we're going to do that right now, okay, to show you what it means. And that might look more harder because you have k and n and 1, 2, 3 and so on. But in practice, it's just a matter of writing out a bunch of stuff. So let me do example 11 to show you what I mean by that. Now, example 11, we're supposed to find the cubic roots. So like I said, if it's a cubic root, then the third root, which means you have 3 answers to be looking forward to. And so then z equals to 8 says 2 pi over 3, which is fine. And so what is the cubic root? Well, following the formula, and then so the z 1/3 equals to will be equal to 8 to the 1/3. That's the easy part. Okay, that is just 2. And then what about the rest of the stuff? I should have probably written it out. I will do that right now. And following the formula, it will be equal to cosine of theta. That's 2 pi over 3, and divided by 2 pi over 3 is the original angle, and then we have divided by n. I'll write the n right here. Divided by n, and then plus the 2k pi over n. Okay, that's the cosine part, and plus I sine part looks the same. I sine of 2 pi over 3n, and plus 2k pi over n. And what that means, that is the answer where k goes, where n, actually n equals to 3. So I could have just written that down. Let me change this to n equals to 3. Okay, so this is 3, not n, because in our case n is 3. So it's 3 times 3, and this n should be 3. Okay, and then this n is also 3. So I should fix that. Times 3, and this n is also 3. They're all 3's. Okay, so but however, what about the k's? The k has to go from 0 to k, where k equals to 0, 1, all the way to n minus 1. N minus 1 in this case is 3 minus 1 equal to 2. So that is the answer. What does that mean exactly? That means that there are 3 answers. The first answer will be, let's see, the first answer will be 8 to the 1/3 is 2, so we'll write that down. So the first answer is 2 cosine CIS, okay? We'll just write down the CIS, and that way we don't have to rewrite everything. The first answer will be k equal to 0. And so the first answer is 2 pi over 9. So it's 2 CIS 2 pi over 9. That's it. That's the first answer, because that's where k equals to 0. The second answer is, again, 2 CIS. Now we have 2 pi over 9 plus whatever's over here with k equal to 1, because k equals 0, 1, and 2. So if k is equal to 1, then it's 2 pi over 9. That part is the same, k equal to 1. Then we have 2 pi over 3. And whatever that and whatever this stuff add up to be, that's the answer. And we'll add it up in a second, maybe. And then the third answer, this part is still the same, 2 CIS. The third answer is, and now k equals to 2. Okay, that's the last k. K equal to 2, then we have 2 pi over 9. That's the first part of the answer. That doesn't change. And then plus the second part, k equal to 2, that's 4 pi over 3. 4 pi over 3. And then whatever this add up to be, that will be the answer for the second part. Well, okay, so now that we've gone this far, what is this anyway? Isn't this part, just the pi part, okay? Just the pi part should be, and that would be 3, that'd be 6, right? 6 over 9 plus 2 would be 8 over 9 pi, 8 over 9 pi. And this part is, again, that's 2 pi over 9, that's 4. Let's see, so that's a lot bigger. That would be, to do the common denominator, that's times 3. 3 times 4 is 12. 12 plus 2 is 14. That equals to 14 pi over 9, I think, if I didn't mess up. I don't know. I could have messed up. But anyway, if you don't mess up that and get the fractions done, we have, let's see. So k equal to 0, we have the, k equal to 0, the answer is 2 pi over 9. That's correct. Okay, I'm looking at the following page at the what the book did. Okay, k equal to 1, then it equals to 2 cis 8 pi over 9 right here. And then the last one is again 2 cis 14 pi over 9. So that is that. Okay, so that is how we will do roots. When you do roots, then you have to formulate the formula and just plug in k as 0, and then 1, and then keep going until you get to the last one. The last one is 1 less than the number n. N is the number of roots you're taking. Like n might be 3 in this case, or n might be 2 or 5, or whatever it is that they want from you. So we have come to the end of section 10.5. For homework, please do page 968, problems 9, 13, 17, 21, 27, 33, 39, and 43. I'm just giving you basically one problem of each type of the examples we've done, and that should be good enough. Because this section is just for you to test the waters of how to use use some basic trigonometric manipulation. Okay, this isn't really to learn complex numbers, so we don't have to go in too much detail. And that should mark the end of this section.